All right, let's pick up our exam review from yesterday. We had gotten just into chapter 20 with the laws of refraction. We said refraction, remember, is what class? Bending of a wave. Specifically, in our case, we were talking about light, so the bending of light. Light is going one way, and then light changes its direction because it has to either speed up or slow down. If the light speeds up, class, how does it bend or refract? Away from the normal. If it slows down. So will the angle of incidence equal the angle of refraction? No. Angle of incidence equals the angle of reflection. Angle of incidence does not equal the angle of refraction. Instead, we had Snell's law that we used for finding the refraction that took place. Again, Snell's law is based on the indices of refraction. That was in our last review lesson. We talked about that ratio of speed of light in a vacuum to speed of light in a particular medium. Snell's law, jot it down, N1 times the sine of theta sub I equals N2 times the sine of theta sub R. We talked about if light is in a high density medium like glass or even water, but glass is a higher density medium, and the light attempts to escape into a low density medium like air. If the light is at just the right angle, it won't get out. It'll stay trapped inside. And so if that happens, we refer to this phenomenon where the light stays in the high density medium as total internal reflection. Total internal reflection, where light refracts so far away from the normal that really just ends up reflecting around inside. Remember, that's the principle of fiber optics. That was the principle used with our laser waterfall thingy, where the stream of water was coming out of the bottle, and the laser beam just kind of went back and forth, zigzagging through that stream of water. Now, for there to be total internal reflection, the incident angle has to be greater than that magic perfect angle that produces 90-degree refraction. What is the incident angle needed to produce 90-degree refraction? That's the critical angle. Anything bigger than critical angle produces total internal reflection. We said they're a transparent object with non-parallel surfaces is called a lens, right? Two types of lenses, depending on what happens with the light. If the light goes through it, it spreads outward. Diverging lens. If light goes through it, it comes together. Converging lens. Now, to be fair, when light rays come together, after they meet, they then spread outward, don't they? Okay, but the diverging lenses just spread out without ever needing to cross over each other first. You will not have lens maker equation on here. Thin lens equation. And this is both mirrors and lenses. Both the mirror equation and the thin lens equation. Now, for the focal length, positive and negative mean two different things. For a mirror, positive means concave, negative means convex. For lenses, positive means converging, and negative means diverging. We don't need to worry about the D sub O, it's always positive. For the D sub I, positive and negative always mean the same thing, real and virtual. However, for a lens, a virtual image is one that appears to do what? Stays on the same side. For a mirror, if it seems to go through the mirror somehow, that's virtual. If it reflects and stays on the same side. So Kendall is here and her reflection is here. That's real. Kendall is here and her reflection seems to be here. That's virtual for a mirror. For a lens, Kendall is here, lens is here. Kendall being on the other side, Kendall's image on the other side, that's real. If Kendall's image still seems to be over there, that's virtual. Talked about myopia and hyperopia. Which one's which? Myopia is nearsightedness, hyperopia, farsightedness. We did also have with this, one more thing. For both mirrors and lenses, have lateral magnification. So that's HI over HO, or negative D sub I over d sub o. Remember, if these two are positive, that means it's upright. Negative means virtual. Just as a reminder, 1 over f. Don't forget the reciprocal at the end, 1 over f. Also for the lateral magnification, greater than 1 enlarged, less than 1 reduced, equal to 1 unmagnified. And that's both mirrors and lenses. We skipped chapter 21 on diffraction or wave optics, including the diffraction patterns and things like that. We went straight to chapter 22 where we talked about electricity. Is that an accumulation of electric charge in an object is called? Static electricity, static electricity. We said that the buildup of charge could be one of two different charges. What are the two types of charge? Positive and negative, okay? Positive charge results from having less electrons, negative charge, more electrons. Of course, if everything's in balance, the object is simply neutral. What was the law of electric charges? Like charges repel, opposite charges attract. The flow of charge is called? Current. And in a solid, how does the current flow? What actually moves? Delocalized electrons. So substances with a lot of delocalized electrons can allow current to flow very easily. Things that don't have delocalized electrons, you're not getting much movement there. What do we call things that have a lot of delocalized electrons? Conductors. Things that don't have any delocalized electrons. Insulators. Very few delocalized electrons. What are the most important semiconductors? Silicon, germanium, and the most important conductors, the best conductors, are in general metals, true, but silver, copper, gold, aluminum. We said if one object has a charge and another body is neutral, if we wanted to transfer the charge, one way to do it would be to take the charged body and have it touch the neutral body. What is that process called? Conduction. Good. What is the result of conduction? Equal charges, diluted charge, same exact charge, right? Equal meaning the same type of charge. If the positive body touches the neutral body will become positive. Negative touches neutral, will become negative. There's another method of charge transfer where a charged body is brought close to the neutral body, but it doesn't actually touch. Induction. And for that to work, remember we said the neutral body would have to be grounded in some way so that the like charge could repel, its like. Pencil down here, I'm stepping on. And of course, for the charge to last, we said what would have to happen to the grounding mechanism? It'd have to be removed in some way. What's a device used to test the charge of a body? Electroscope. We said like charges repel, opposite charges attract. For like charges to repel, there must be some force of repulsion. For opposite charges to attract, there must be some force of attraction. And there was a guy who noted that the force of attraction or repulsion is proportional to the product of the absolute value of the charges, but is inversely proportional to the square of the distance between the charges. Who came up with that equation? We actually named the unit of charge after him. Coulomb. Coulomb's law of electric force. Coulomb's law of electric force. And you know that the SI unit of charge is the Coulomb. K, by way of reminder, has a value of 8.99 E9 newtons times meters squared per Coulomb squared. Electric field strength will not be on the test. We skipped magnetism. It's cool to talk about. We just didn't have time. Something about a senior trip y'all wanted to take. Want to sit at the airport for a long time. Oh wait, that's skipped over batteries and AC generators and electromagnetic induction, all cool stuff. But we wanted to get to pathway for current. A pathway for current is called? Circuit. Circuit that uses a battery is a DC circuit, because all the current goes in the same direction. And then anything that runs off the, plugs into the wall is going to run off of AC, because the power plants are AC. By the way, do you remember who it was that invented the light bulb, the electric light bulb? Thomas Edison. It wasn't the guy who discovered electricity or anything like that. Benjamin Franklin is credited here in America with kind of being the father of electricity and stuff like that. But Edison was the electric light bulb guy. He did not like this whole AC stuff. He said it was too risky, produced too high of a voltage, he made him nervous. But you just can't make batteries big enough to actually power homes. You've got to have it. So risks aside, AC is the way to go, and that's what we use for something plugging into the wall. I mentioned that AC produces really high voltage. Remember we said voltage basically is what pushes the current through. Current, again, we said is just those delocalized electrons. Voltage is what pushes them through. Why is a push necessary? Why don't the electrons just go flying around on their own? There's blockage called interference. Not called interference. Resistance. And remember we said to find resistance in a wire, there are three things that cause resistance in a wire. Or affect resistance. The thickness of the wire or the cross-sectional area. The type of material, the resistivity of the material. What's that wire made out of? Temperature. Not the temperature. Well, technically temperature does have an effect on resistance, to be perfectly fair. The length. The longer it is, the more resistance there's going to be. The bigger and thicker it is, higher gauge, or technically lower gauge, the thicker it is, the less resistance you're going to get, and then of course the resistivity affects it as well. Quick reminder, on the cross-sectional area, it's going to be in centimeters squared, and usually you're going to use pi r squared to find that cross-sectional area. Length will be in centimeters, resistivity in ohms times centimeters, because the SI unit of resistance is the ohm. We said we could actually use resistance to our benefit in a couple of ways. For one thing, resistance can be very helpful if you've got a lot of resistance and you've got a lot of voltage pushing current through, because high resistance and high voltage can produce heat. Heat can be good for us. Now, if it overheats and burns something, that's bad, but heat can be useful for cooking, warming our homes, drying our clothes, all kinds of stuff. So resistance isn't always a bad thing. Other times, we might be able to adjust resistance at times. What do we call an adjustable resistor? A rheostat. A rheostat. Remember volume control, dimmer switches, temperature controls, all of those are things that use rheostats. They adjust the resistance to change what comes out. If we were to take some conductive material and lower its temperature way down near absolute zero, what would we be making? Superconductor. Superconductor. Again, we said a pathway for current is called a circuit. For a DC circuit, we said there are three things that need to be there. There need to be loads of some kind, something or resistor, something that uses the current. It's got to be the pathway to begin with, right? So we need some wires, some conductors. We got to have the source of the current, or the battery, the thing that starts it all moving, the thing that pushes it all through with voltage. Ohm's law equation, something we have used a lot. V equals IR. We use it all different ways, right? We use it I equals V over R, V equals IR. Technically, we could use it R equals V over I. We just usually don't need to for our circuits, because resistances are usually spelled out for us. But V equals IR, again, V is voltage, I is current measured in amperes. And the R, of course, is resistance measured in ohms. We said that for a DC circuit, we could arrange the resistances or loads different ways. If we have the current going through one resistor, then the next, then the next, then the next. Series. If we have it going through all the resistances at once, because there's multiple pathways. Parallel. If you have series and parallel together, it is a network. Good. Whew, we do not have a lot of time here. Flip in your books real quick to page 291. Page 291. Spent a little longer going over that quiz than I had anticipated, and it ate up some time that I needed for review. Page 291, for sake of time, we won't work the problem, but I want you to look at problem 9. You might write this down in your review notes. This might be a good problem to work on your own. Mirror problem, right? An object 6 centimeters high, okay, there's your H sub O, is located 12 centimeters, there's your D sub O, from a concave mirror with a radius, there's your R, of 20 centimeters. Remember, for a mirror, the focal length is half the radius of curvature. So if the radius is 20 centimeters, what's the focal length, class? 10 centimeter focal length. Find the position, size of the image, and the lateral magnification. Describe the image. That used all of this stuff here. Okay? So this stuff, I'm going to let you kind of play with that on your own. We'll hopefully have time to look at this. I think we will have time to look at this tomorrow before the test. But page 291, number 9, is a good example of the type of thing you might see on your test. Flip over to page 308. Page 308. Problem number 18, very similar. Object 3 inches high is located 10 inches in front of a converging lens with a focal length of 12 inches. Find the position and size of the image and describe the image. All right, so page 308, number 18, also uses this, but for the mirror, or rather for the lens, would be a good problem for you to be working. Flipping over to page 340. Page 340. Look at problem number 2. Problem number 2. We've got a couple of charges. One's positive and one's negative. They're located at a certain distance from each other, and the question is, how much force do they exert upon each other? Force of attraction. Well, since it's attractive force, we would get a positive. Again, we plug in those numbers. That would be a good problem to work. Flip over to page 398. Page 398. Problem number 2. We've got a little wire. They give us the diameter and the length and the material, and they want to know how much resistance is inherent in that wire. That would use this equation. Problem number 4, just below that. Go down a couple problems. Problem number 4. They give us voltage, they give us current, they want resistance. That would use Ohm's law equation. So page 398 has 2 problems on it of note, problem 2 and problem 4. I'm going to draw them. We're going to look at these tomorrow as well. A couple of networks that if you wanted some extra practice, wouldn't be a bad thing to be solving them, but this will give you the opportunity to work them in advance. So stay with me for just a second. Draw a couple networks up here for you to practice, similar to what you might see on the exam. We have an 18-volt battery, current going through a 2 ohm resistor, and then splitting into a 6 ohm resistor and 10 ohm resistors in parallel. Current then flows through a 1 ohm resistor, and on the way back to the battery encounters one final resistance of 3 ohms. Okay, so this would be something similar to what you might see tomorrow. Also, you have a 9-volt battery. Current goes through a small 1 ohm resistance, travels through a 4 ohm resistance, then through a 2 ohm resistance back to the battery, but we add an additional pathway that has 3 ohms and 5 ohms. These are the 2 we're going to work tomorrow. Now, none of this is homework. The plan is, in the short time we have before the exam, to try to go over all of this math very quickly. But you will benefit if you go over this math on your own first. All right, have a wonderful rest of your day. We'll look at all of this tomorrow, and then we'll take that exam. Have a great day.